In this context, the decay time is very short. If it were long, it would delay the process or reduce the effectiveness of the crystal. You need this electron decay time to be very small so that you can start taking the next photon and the subsequent ones. The third property is that you can stop the photon. The decay time of this electron should be fast, and the light fraction or the light photons emitted should be large. The fourth point is that the photoelectric interaction ratio occurring within the crystal should be better or higher than the Compton scattering to improve resolution and avoid scattering photons that could affect image quality. These are the properties based on which the crystal is selected. It is determined based on whether the resolution of the crystal is good and what its sensitivity is. In fact, this topic is very important when choosing any machine. We hear about a company that produces bismuth germanate and another company that produces lutetium oxyorthosilicate. Each type has specific properties. As someone buying a machine, I need to understand where the sensitivity is high, where the light fraction is high, and where the decay time is fast among all the crystals. They have a great table here. Let's return to this topic. Crystals come in various forms and compositions, each with unique properties and applications. For instance, sodium iodide is often used in radiation detection due to its scintillation properties. Bismuth germanate, also known as PGO, is another type of crystal that is valued for its high density and effective gamma ray stopping power, making it useful in medical imaging and high energy physics experiments. Additionally, lutetium oxyorthosilicate, abbreviated as LSO, is a crystal known for its excellent light output and fast decay time, which are crucial for precise timing in positron emission tomography (PET) scanners. These examples illustrate the diversity and specialized uses of different crystal types in various scientific and industrial fields. In bismuth germanate, the decay time is about 4200, and in lutetium oxyorthosilicate, it's around 13,000. How much is the decay time here? 300 nanoseconds, which means the electron takes about 300 nanoseconds to drop and produce the light photon. How much does it take here? 47. Okay. Forget about the index and fraction. That's not our concern. The attenuation coefficient here is 0.96 for bismuth germanate and 0.88 for lutetium oxyorthosilicate. The photoelectric effect in bismuth germanate is higher than in the component. That's why you find bismuth germanate and LISO both have some aspects where one is better and the other is worse. For me, as Islam, when you ask me about the most important things, light output is very important, and decay time is also very important. What about the decay time? Do you see the difference here? A 47.3% decay time can significantly affect your resolution. That's why you find that the resolution in LSO or lutetium oxyorthosilicate is higher than the resolution in bismuth germanate, while bismuth germanate has better sensitivity, even though the light output is 4,200. However, the photoelectric ratio is higher, and its attenuation coefficient is also high. It closes the photons that fall on it better than lutetium oxyorthosilicate, which gives you a higher sensitivity. That's why they always tell you, if you want resolution, go for lutetium oxyorthosilicate. But I also want to understand why you mention the decay time here, because when we talk about resolution now, you'll find that this topic is very significant. So let's focus together. Before we delve into the specifics of our discussion today, I am pleased to introduce the esteemed doctors from Thamani, who are here with us. To start off, I would like to present this particular item that I have brought along. It is significant to our conversation and will serve as a focal point for our upcoming dialogue. The ligand, or the thing that produces the free energy where the positron is, if everything is going ideally. A photon moves like this. A photon moves like this. The crystal gives me the image. Everything looks good. There is no problem at all. But what is happening? The world must have problems with the photon. As it exits, it might move in this direction and undergo Compton scattering, and it could be detected in that upward direction. This is likely to happen. In the field of physics, particularly quantum mechanics, the behavior of photons is complex and intriguing. When a photon exits a medium, it can travel in various directions. One phenomenon it may experience is Compton scattering, where the photon interacts with a particle, such as an electron, resulting in a change in direction and energy. So, if I have these two detectors that detected the two gamma photons, I call it coincidence. This coincidence is a true event. There is no problem at all in this case. This is a true coincidence for me. In the case where this photon is received by this detector, the second photon was supposed to go to the opposite detector, but it had an interaction here and became scattered, reaching the detector. So, the line of response that is calculated, which is what the machine will calculate, becomes a dashed line. Consequently, when I try to localize the annihilation location, it will be in the wrong place. I call this scatter coincidence. Here, for example, I have one ligand present and another ligand present, one emitting here at 180 degrees and the other the same. So what happened is that I have a ligand here at 180 degrees. A light photon, for example, hits this detector, and consequently, my machine here starts calculating. It starts calculating that this photon came as scattered. So it comes down here, and on the other side, another ligand is coming from a different place. What will happen is that it will start calculating its line of response, and it will begin to indicate the location of the point here in this dashed point. But this is not true. So it creates something called random coincidence. The true event, which is the first one, or the true coincidence. There is something called a single event. What does single event mean? It means a detector receives a photon, but the detector that is supposed to receive it does not. So, I call this a single. I call it single. The true event indeed occurs when both detectors collide with something, leading to a complete chaos in the collection. The random event for me comes from two different locations. Both reached each other, but one of them is coming from one location and the other from a completely different location. However, due to the scattering that occurred, they reached each other. Now, does what we are saying create a problem for the localization of the annihilation? The annihilation is the place where the collision occurred between the positron and the electron, which is where your radioactive material is located inside the patient, right? There is a true event or true coincidence here, and I have no problem with that. But with the disc cutter, and the random will the determination of the location from which the radioactive material came be done correctly or incorrectly? Incorrectly, I need to do something to overcome this issue. What did they tell you to do? The first thing you can do is the pulse height analyzer. Do you remember what the pulse height analyzer did? It provided you with an energy window for the scattered photon coming into the detector. Is it going to come with the same energy of 511 or less? It's less. Why less? Because when it underwent Compton scattering, what is Compton? Compton is when the photon, while exiting, gives part of its energy to the electron and it undergoes scattering with part of the energy and it exits with 511. Therefore, when it undergoes scattering, its energy will naturally be less than 511, right? Because it gave part of its energy to the electron. So here, if I tell the detector, hey detector, only do detection within a certain range of energy. Just like I set it to 140 kilo electron volts with a plus or minus 10% or 20%, here the same idea applies. I will tell it to work on a specific energy window. In this case, any photon coming to me that is scattered, will I detect it or not? I will not detect it. But who is it, Dr. Hani? It is a scattered photon that underwent Compton interaction. So, what about that? I dealt with the listeners, but Tarek, I dealt with it. Now look, focus with me. If I am coming to you, for example, if annihilation occurs here and I have another leg, one will come out here. And as the other one exits, Compton scattering happens and goes to a different detector. No problem. This detector will consider this as scattered radiation, so it will remove it from the window for me. But there is a leg here. This leg emits photons in all directions, and this is a range, so it can reach here at 511, right? Is that a lot or a little? And how many are coming here? 511 as well. What will the detector do with its energy? How will it handle it? Do you understand the problem, or should I repeat it again? First, in the region or the place where there is a radioactive material, do photons come out in all directions or in one direction? In all directions? In all directions? Yes, there are two photons at 180 degrees. But those 180 degrees can be like this, or like this, or like this, in any direction. I don't know how they will come out, but they are both at 180 degrees, okay? So if I have region 2, that's it, and I have here. Here is a detector, and here is another detector, and here is a detector over here, and here is another detector. The expectation is that this leg will produce two gamma photons. One will move in this direction, and the other is supposed to go to this detector. However, while it is moving, it experiences Compton scattering. Now, the leg next to it has radioactive material, which will emit gamma photons in all directions, as we agreed. So, it is expected to emit a photon like this, and another photon, for example, like this, which went to this crystal. So, something like this happened. It underwent Compton scattering and moved like this. So what happened is that I now have two detectors. So, they received two gamma photons, both at 511. But the two came from different places, right? How can the detector handle them? How can the detector handle them? We all say, it depends on the energy. I mean, the riser will handle it, but it depends on the energy. Now something new has come up called timing resolution. This new development in timing resolution is a significant advancement in the field. It tells you that I will do a pre-adjustment for the detector, making it clear that this detector is, in the name of God, the most gracious, the most merciful. It provides a more precise understanding and control over the pre-adjustment process for the detector. This ensures that the detector operates with the utmost accuracy and efficiency. I perform a pre-adjustment for the detector and say to it, when a photon comes to you indeed, this photon has an energy of 511. The detector will only register this photon when the opposing detector receives a gamma photon of 511 energy, but within a time frame not exceeding 1 nanosecond. So, what have I done? I have achieved timing resolution. It means I worked on time as a factor affecting what? On my ability to ignore the signal coming to me or the gamma photon coming from another place with the same energy, but arriving at a time far from the time of the photon that came in the detector. Do you understand? Do you understand how to do localization now? What? It is capable of achieving good localization of the activity's location. It is directly related to the quality of the localization process of the place. Yes, of course. It can achieve good localization because, Dr. Hani, what I'm saying is that this is a probable scenario. You are detecting millions of gamma photons, so a certain percentage of true events can occur. Your imaging relies on what? On the true events for you. Will true events not occur at any location with radioactive material? They will occur. But your role is to eliminate the scatter and the random scatter through energy resolution, and the random through timing resolution. So, in the same location, even if this detector does not accept it, it can still be detected by another detector in a completely different direction. So, can it achieve localization with me? Yes, exactly. Is that clear? Yes, it's clear. So, I have eliminated the scatter and the random, right? This will improve the resolution of the image, of course, and the localization of the activity or the position of the region of interest. All right, that's good. Now, there's a point to consider. Good. So now we know what we know, and we know how to remove the scatter and how to remove the random noise. We also learned that the 2 detector relies on the energy window and timing resolution to detect incoming signals in a short time. Do you remember when I told you that the decay is about 47 nanoseconds? Well, doesn't that help you reduce the time window? Does it help with timing resolution or not? Does it give you high resolution or not? Do you remember when I told you that the electron takes a short time to descend? This time helps me when I reduce the time window, allowing it to make a detection. In this case, I will quickly receive the signal because the electron will descend quickly and then the next one will come. So during this time, I can shrink the time window, which in turn improves the resolution. That's why the LISO is considered to have a higher resolution than the PGO. Now, Let's talk about something else. The two gamma photons that are emitted. First, I have FDG, gallium-68, and rubidium. I have different isotopes used today in imaging. All of them emit positrons, but the positron that comes out, doctors, I'm not talking about gamma rays or the annihilation process. Do all the positrons emitted from FDG carry the same energy as those from gallium or rubidium? You said no. The positrons from FDG have the lowest energy. So, how does this matter to me? I will tell you how it matters. It significantly affects something called resolution. How? Let me explain. I'm saying that the location of the radioactive material is where a positron is emitted. This positron, as we said, travels a bit, right? So the annihilation point is not the same as the location of the radioactive material. It's several millimeters away. If this positron has high energy, will the distance it travels be large or small? Large. Large. This is what happens with gallium-68 and rubidium, where the energy of their emitted positrons is high, allowing the positron to travel a greater distance before annihilation occurs. In contrast, with FDG, for example, the distance is small, so annihilation happens closer to the source. Consequently, this affects the resolution. Of course, this distance is in millimeters, just so no one thinks it's large, as I mentioned. But the resolution will be affected by the positron energy, which is referred to as the positron range, the range in which the positron moves. If the positron moves further away, the location of the annihilation will be affected, which will impact the accuracy of localization when determining the location of the activity or the radioactive isotope. This is referred to as the positron range. Additionally, it was mentioned that the two gamma photons emitted are not exactly 180 degrees apart. He told you there is something called collinearity because the positron is in motion and the electron is in motion, so neither is at rest. Collinearity occurs with two particles. Both are annihilated. Due to this movement, they have momentum, which is referred to as momentum force. This momentum force causes the angle of annihilation to be 180 plus or minus 0.25 degrees, meaning it is not exactly 180. So what does this mean? It also affects your resolution and the localization of the annihilation point. I call this collinearity. The linear coefficient is very good. So we are talking about the various factors that affect the different images of the patient. Another important thing you should also pay attention to is that I have a range of detectors. The ring of the detector is shown here in this image. This is the shape of the detector ring, and this is the shape of the patient. The ring, of course, allows the patient to enter inside it, and it has a specific field of view. This field of view is oriented towards the patient, meaning it has a certain width and a specific field of view in that direction. So, when imaging the patient, for example, the whole body is captured from the head to the upper knee or just after the mid-femur. You take this width, which is referred to as the area you are imaging. You take images of a specific area, and then the device moves to the next area. So you have it divided into blocks like this. You take images, then move to the next block, and then move to the next one, continuing this way. It depends on how many rings you have here. you see this view. This is your ring. This is one ring. And this square or block that you see here is called a block. This is where the crystal is. And behind it are the photomultiplier tubes. The shape of the squares you see here is the crystal element. They call it elements. And around it, there are 4 photomultiplier tubes. So this is the block for you. And this arrangement is the arrangement of the ring. You might have machines with 1 ring, 2 rings, 3 rings, or 4 rings. The larger these rings are, look at how the view will be. In the name of Allah, the most gracious, the most merciful. Look, here is the range. This is 1 ring, this is 2 rings, this is 3 rings. So you are covering a large area in the body of the patient at once. Now, do you expect the coverage in the extremities to be the same as in the center of the ring? The resolution at the periphery will be different at the extremities.